I hope my screen is visible to everybody. Yes? Someone please respond. Is it visible?
Yes, sir.
All right then. Okay. So we will start now. So we have successfully completed the analysis of 1D bar, and there we have seen how to analyze the bar having different cross section, different material or material of modulus of elasticity, you can say. And we have also seen how to take care of the loadings. We have also seen the analysis of beams also. So now moving ahead, now we will be going for the analysis of two-dimensional problems. Okay. So before going for actual analysis, we have to define or we have to derive the stress strain relationship for different types of problems which are used in the finite element method, right? So basically, what is happening over here is, in case of, let us say, 1D problem, okay. So you know that the K matrix for 1D problem, it is nothing but integration over the volume. Then we have a B transpose into D into B over dV. Okay. So where this D is nothing but your stress strain matrix. Okay. Okay. For 1D problem, so so for 1D problem, this D matrix is nothing but your E. Okay. So E is what? E is nothing but the modulus of elasticity for a given material. So as per Hooke's law, what is happening over here is something like this. The material behavior is considered to be in form of a straight line. Okay. And that straight line is like this. Okay. And the slope of this straight line, this will be called as your E. So here you have strain, here you have stress. Okay. So the slope of this particular line is nothing but stress divided by the strain. Okay. And it is assumed, as per the Hooke's law, the stress strain relationship is constant, and it is within the elastic limit. That's why we are considering the value of E as D. Okay. That is a stress strain matrix. Now, as far as two-dimensional problems are concerned, so for two-dimensional problem, there are different categories. Like for example, let us say we have a beam. Okay. So in the previous class, we have seen that this beam can be analyzed as a 1D problem. Okay. But if you see the real life picture of the beam, it looks like this. Okay. We have a three-dimensional beam. Okay. So this is a three-dimensional beam, you can say. So it looks like this. Okay. So now if this is a three-dimensional beam, so this can be analyzed as a 2D problem. So while going for analysis as a 2D problem, so you will get only two things. Okay. One is the length of the beam, and second one is the depth of the beam. Okay. So this becomes a 2D problem. The third direction, we have only the thickness, right? So that way we can analyze this particular problem. So as far as the three-dimensional analysis is concerned, we can have categories of or two-dimensional problems as plane stress problem. Okay, this is one, that is plane stress condition. Okay. Secondly, uh, secondly, we can have plane strain condition. Okay. So this is, okay. And thirdly, we can have axisymmetric condition, AXI. Okay. So here also I should write condition, right? So there are three different types of problems, or the given problem can be categorized as either a plane stress problem or a plane strain problem, or maybe a axisymmetric problem. Okay. So now let us try and understand what is your plane stress problem. Okay. So let me write down over here what is your plane stress problem. Okay. So for example, we have a simple plate. Okay. So let us say this is a simple plate. Okay. Which is having some dimension. Let us say this is the length of the plate and this is the height of the plate. Okay. So we will also have a certain thickness. Okay. So this thickness will be, in case of plates, this thickness will be very, very small. Okay. So I'm saying very, very small because as compared to the other dimension like L and E, they are relatively very small. So let me draw a straight line like this. Okay, so you can see this is a simple plate. Okay, so if you see this thickness, okay, so this thickness is very small as compared to the height of the plate and as compared to the length of the plate. Okay, so such type of problem where the third dimension is very small as compared to the other two dimensions, so such type of problems can be categorized as a plane stress problem. Okay, so what is difference between a actual 3D problem and the plane stress problem is that since the thickness is very small, okay, so in that particular case you will it is assumed that the stress in the third direction, generally we write the third direction as z direction, so it is assumed that the stress in the z direction as zero. Okay, ideally it is not zero, it is very small, but for sake of analysis what is assumed is that the stress in the third direction is very small. Because of the nature of the problem, the thickness in the third direction is very small. Okay, so now what is the use of considering the stress in the z direction as zero? Okay, before going for that, since the stress in z direction is assumed to be zero, so the corresponding shear stress, that is the tau x and z, as well as the tau we can say y and z, okay, both will be zero because the third direction stress is zero. So the shear components involving the third direction, they will be also zero. Okay, so now just going for the derivation of the uh, uh, stress strain matrix for a plane stress condition, what we have to do is we have to first of all refer the some of the basics from the from the theory of elasticity and the strength of material, right? So if you remember in the theory of elasticity, you might have studied the stress tensor, okay, where you have a 3D box which are having the different kind of stresses, sigma x, sigma y, sigma z, and we have shear stresses also, shear that is tau xy, tau yz, and tau zx. Okay, so if you refer those expressions, so in that case what you will get, you have standard equations ready for you from the basic principles of strength of material. So the epsilon x, okay, that is the strain in the x direction. Okay, so here let me draw the axis first. So here this will be your x axis, okay, and here this will be your y axis, and the third direction this will be your z axis. Okay, so if this is the condition, then the epsilon x value can be calculated as sigma x divided by E minus mu. So mu is nothing but your Poisson's ratio. Okay, so this Poisson's ratio is there. Then we have sigma y divided by E, that is the modulus of elasticity of the material. Then we have sigma z upon E. Okay, I hope you remember this expression. Yes, student, do you remember this? Yes, somebody please respond.
Yes, sir.
Hmm? So this is already covered. So let me write down the expression for the epsilon y also. So epsilon y can also be written in form of a similar expression to the epsilon x. So this is sigma x upon E minus we have mu times we have sigma x upon E plus sigma z upon E. Okay, and again we have one more expression, and that expression is for epsilon z. So epsilon z can be written as sigma x sigma z upon E minus mu times, here you will be having sigma x upon E, okay, plus sigma y upon E. Okay, so these three expressions are there with you. Okay, similarly we have some expression to calculate the shear strain. Okay, so shear strain can be written as gamma. So gamma xy, now this can be written as tau xy divided by G. So where G is nothing but your modulus of rigidity. In the similar pattern, we can write the value of gamma yz as tau yz divided by G, and similarly we can write gamma zx as this is tau zx, okay, divided by G. Okay, and I hope everybody remembers the expression for G. G is the modulus of rigidity and G can be written as a E divided by 2 times 1 plus mu. Okay, so these expressions you are already familiar with. Okay, so using these 6 expression plus this G expression, that is 7 expressions, now we are going to generate the stress strain matrix or a D matrix. Sometimes in some books it is also called as the constitutive matrix. So we are going to generate this for the plane stress condition. Okay, so now let us quickly see the derivation of this matrix in the plane stress condition. Okay, so like I said earlier, in the plane stress condition, the thickness in the third direction is very small. Because of this, the stress in the z direction is considered to be zero. It is assumed to be zero. Okay, so now if we are assuming the stress in the z direction as zero, okay, so let me write down over here. So here I am saying that the assuming, okay, so I'm assuming the stress in the z direction as zero. Also I am assuming the stress, shear stress in xz direction as zero, and the shear stress in yz direction as zero. Okay, so this is my assumption. So if you assume this particular thing, in that case what will be your epsilon x? So if you refer this particular expression, so this is the expression for the epsilon x. So in this expression, the stress in the z direction will be zero. Okay, so in that particular case, what will be epsilon x now? So epsilon x will be sigma x upon E, okay, minus mu times, you will have only one term, that is sigma y upon E. Okay, because the other component will be zero. Okay, so similarly you can write even the values for the epsilon y also. Okay, so here we have the epsilon y values. Okay, so we can rewrite the same thing over here. So let us say we have epsilon y equals to sigma y upon E minus, now you will have mu into, you will have sigma x upon E. Okay, so now you have two expressions with you. One is for epsilon x and one is for epsilon y. Okay, so let us call this as expression number 1 and this as expression number 2. Okay, so now what we can do is we can solve this above two expression, that is expression 1 and expression 2, and we can get the value of sigma x and sigma y in terms of epsilon x and epsilon y. Okay, so right now what is there with you, that is like you have epsilon x which is written in terms of sigma x and sigma y, and epsilon y which is written in terms of sigma x and sigma y. Okay, so I'm just solving both these expressions. Okay, so I, after solving this expression, what I am getting is something like this. Okay, one is sigma x will be equals to, this will be E divided by 1 minus mu square, okay, into, we have epsilon x plus mu times epsilon y. So this is one expression you will be getting, and you will be getting another expression, that is sigma y will be equals to something like E divided by 1 minus mu square into, here you will get something like mu into epsilon x plus epsilon y. Okay, so just solving these two expressions, now you can get two expression, that is expression A and expression B. Okay, is it clear, student? Any questions as far as this part is concerned? Yes, somebody please respond. Yes, is it clear to
No, sir.
everybody? Sorry.
Yes, sir.
Okay, fine. So what I'm going to do, we also have one more expression. Okay, so since if you see over here, the two shear terms, that is tau xz and tau yz both are zero. How about tau xy? It is not zero, isn't it? So what I can write, I can assume the, or I can use the similar expression which are given above. So I can write something like tau, oh sorry, the gamma xy now can be written as tau xy divided by g. So this one expression is there with me. So let us call this as expression number C. Okay. Rest of the expressions like sigma z is already 0. This is what we have assumed. So now we have assumed three expressions to be 0. Sigma z as 0, tau xz is 0, and tau yz is 0. So rest of the expressions, they are not 0. So now we have the values of sigma x, sigma y, and sigma z. Okay. So now what I can do is I can rewrite this expression to calculate the value of tau xy. Okay. So here the same expression I am writing down over here. So tau xy now can be written as g into gamma xy. Okay. And we know the value of g as e, okay, divided by 2 into 1 plus mu, okay, and into, now you will have gamma xy. Okay. So now we have one more expression. Okay, this is, let us say, d expression. So this a expression is showing you the relationship between sigma and strain. This expression is showing you the sigma y, relationship between sigma y and strain, and this expression is showing you the relationship between the shear and the shear strain. Okay, shear stress and shear strain. Okay. So now what I'm going to do is I need to do some normalization over here. Okay. So what I can do is tau xy now can be written as something like 1 minus mu square divided by 1 minus mu square. Okay. So this is going to happen because if you solve this numerator and denominator is going to cancel, and ultimately you are going to get this thing as 1. Okay. So then I am writing down the same expression, that is e divided by 2 into 1 plus mu, okay, into gamma xy. Okay. I can write this because ultimately this is going to get cancelled, right? So now if you expand this particular expression, 1 minus mu square can be obtained by simply going for 1 minus mu into 1 plus mu. Okay. So I can write the same thing over here, and then the denominator part will remain same, that is 1 minus mu square, and this will be e divided by 2 into 1 plus mu into gamma xy. Okay. So now you can see there is one term which is common, that is a term which is over here. This is 1 plus mu, and here this is 1 plus mu. So this can get cancelled, and as a result of this you can get tau xy as something like, I'm just writing down e divided by 1 minus mu square. Okay. So which is basically this term over here. Okay. Okay. So this is this term, and then we have this particular term. So I'm taking out these two common, then multiplied by, I can simply say something like 1 minus mu divided by 2 into gamma xy. Okay. So let us call this as expression number e, right? So now if you refer the three expressions which are written over here, the first expression, that is sigma x expression, okay, then we have sigma y expression, then we have tau xy expression. In all these three expressions, what you are getting is 1 divided by, sorry, e divided by 1 minus mu square as a constant. Okay. So I can rewrite the entire terms. Okay. So I'm just writing down all the terms over here now. So I can write something like sigma. Okay. So this is a simple stress vector. So stress vector in 2D case, it will be consisting of sigma in x direction, sigma in y direction, and the shear in xy direction. Okay. So we already have the expressions for sigma x, sigma y, and tau xy. So if you refer this sigma x, we have one constant, then it is multiplied by 1 into epsilon x plus mu into epsilon y. So the same thing, let me write down over here first so that I can explain afterwards. So I can take out this common, that is 1 minus mu square, and here you can have something like 1 mu 0, here mu 0, this will be 1, this will be 0, this will be 0, and here I am writing 1 minus mu divided by 2 multiplied by, now you can have here as epsilon x, epsilon y, and here you may have gamma xy. Okay. So now if you want to calculate what is the value of sigma x, so sigma x will be nothing but this particular constant into 1 into epsilon x plus mu into epsilon y. So here you can see this is 1 into epsilon x plus mu into epsilon y, and there is no term of gamma xy. Okay. So similarly, you can see expression b also. So in expression b, the value of epsilon, sorry, sigma y can be calculated as this constant. So this constant is common everywhere. Then this will be mu into epsilon x plus 1 into epsilon y. So here you can see mu into epsilon x plus 1 into epsilon y. The constant is there outside. So lastly, we can have the tau xy term. So tau xy term, you can see e divided by mu square is constant, which is outside. It will be 0 into epsilon x plus 0 into epsilon y plus 1 minus mu by 2 into gamma xy. So this is the relationship, or this is a matrix which is showing the relationship between the sigma, that is stress, and the strain. Okay, so that's why this particular matrix is called as a stress strain matrix. Okay, so in short, what I can write over here is like this. Okay, so this particular matrix, okay, this particular matrix is nothing but your D matrix. Okay, so the same expression now can be written as this is sigma equals to D, okay, into this is strain. So this matrix is nothing but your stress strain matrix. Okay, so stress strain matrix means what? There is on the left hand side we have a stress, on the right hand side we have a strain. So for 1D case, okay, remember for 1D case, sigma is nothing but E into strain. Only we have only one term over here, that is epsilon x and epsilon sigma x, and here we have epsilon x. But in this case, in case of 2D, this will be having three components. One is the epsilon sigma x, second one is the sigma y, and third one is the tau xy. Okay, so this is the expression for the plane stress condition, where the stress is assumed to be constant in the z direction. Okay, is it clear to everybody? Are there any questions? Yes, are there any questions, please? Yes, students, shall I continue?
Yes, sir.
Yes, sir.
Fine. So this is the expression for stress strain matrix for the plane stress condition. Okay, so now let us talk about another type of condition which can be seen in case of 2D problem. Okay, so let me put a straight line over here. All right, so let us talk about the plane strain condition now. Okay, so right now, a plane strain condition is a condition wherein the third dimension as compared to the other two dimensions, it is very, very large. Okay, it is exactly the reverse of the plane stress condition, right? So in plane stress, what happens? The third dimension is very small. So the example was a plate. Okay, but in case of the plane strain condition, the third dimension is very, very small. Okay, so one of the best example of this plane strain condition is your dam. Okay, so let us say this is your dam. Okay, so in this dam, so the third dimension, okay, so this dimension is very large. Okay, so basically this is nothing but your thickness. Okay, so this thickness is very, very large. Okay, no, not this symbol, this should be, this is very, very large as compared to the other two dimension, that is B and H. Okay, so let us assume this is nothing but your B and this is nothing but your H. Okay, so in real life problems you will find let us say in this particular case your width may be something like 3 meters or maybe 4 meters, the height may be also 3 meters or 4 meters. But if you see the third dimension, this can be even 30 meters or 40 meters and so on. Okay, so basically the third dimension is very, very large in the plane strain case. Okay, so now since the third dimension is very, very large, so because of this the strain, that is the change in length upon the original length. Okay, so because of the loading condition, the possibility of strain coming in the third direction is very, very less. Okay, because you see here you will be having a water pressure and because of this your structure may be deformed like this. Okay, but as far as this direction is concerned, the deformation is not at all possible. Even if it is possible, the value of this strain will be very very small. Okay, so because of this, in the plane strain condition, the strain in the z direction is assumed to be 0. Okay, why? Because the third direction is very small, and sorry, third direction is very large, and since it is very large, the possibility of getting deformation in the third direction is very less. Even if it is less, the magnitude will be very small. Okay, that's why we are assuming that the strain in the z direction is 0. Okay, so this doesn't mean the stress is not 0. Okay, stress will be there, so don't worry about that. Okay, so now in the earlier case also, in the plane stress case also, in the plane stress case, we have assumed the stress in the z direction as 0. So this doesn't mean the strain is 0. Strain will be there, because there is an expression for strain by which you can calculate the strain in the z direction. So in this case also, the strain is 0, but the value of stress will be there. Some value of stress will be there in the third direction. Okay, so now since the strain is assumed to be 0 in the third direction, so corresponding strain in the relative direction, that is x z, and the strain in y z, they will be also 0. Okay, so with this little information, now we can generate the expressions for uh, the stress strain matrix. Okay, so now what is assumed to be 0? That is sigma, sorry, not sigma, the strain in the z direction is assumed to be 0. Okay, so if you remember, the strain in the z direction can be calculated as sigma z upon E minus, I have written plus, sorry for that. So this is minus mu into, we have sigma x upon E, okay, plus sigma y upon E. Okay, so this is one expression, and this is assumed to be 0 over here. Okay, so now what I can do over here is I can rewrite, or I can transfer this term over here. Okay, and then I can cancel the value of E. Okay, because E will be constant. So if you solve this expression, so what you are going to get, that is sigma z is nothing but mu times sigma x plus sigma y. Am I right? Is it correct? Yes, student, is it correct?
Yes, sir.
So I am getting one expression. So let us call this as expression number 1. Okay. So sigma x, oh sorry, sigma z can be calculated as mu times sigma x plus sigma y. So see over here what we have assumed, that is the sigma z is 0, but here sorry, epsilon z is 0. This is what we have assumed, but still you are getting the value of sigma z, that is the stress in the z direction. Okay. Now similarly, using the basic expressions, now you can have the values of sigma x and sigma y. Okay, so let me write down over here. So your sigma x, okay, so your sigma x, this expression can be taken from the earlier expressions, right? So sigma x can be written as something like E divided by let me go back. So sigma x is something like E divided by 1 minus mu square. Okay, this is into epsilon x plus mu times epsilon y. This was the expression, and we have sigma y equals to E divided by 1 minus mu square into, this is mu into epsilon x plus uh, sorry, this is not the expression, by mistake. I have written wrongly over here. Let me undo this. Okay, this is not the expression, sorry for that. We have two basic equations from the strength of material. Okay, let me write down those. Okay, so okay, so I'm just writing something like epsilon x equals to, we have sigma x upon E, okay, minus mu times, we have sigma y upon E plus sigma z upon E. This was the first expression. Then x epsilon y can be written as sigma y upon E, okay, minus mu times we can write sigma x upon E plus sigma z upon E. So this is another expression. And epsilon z, okay, so this is epsilon z can be written as sigma z upon E minus mu times we have something like sigma x upon E plus sigma y upon E. Okay, so these are the basic expressions. So now what we can do is we can solve these expressions for sigma x and sigma y the way we have solved earlier case. Okay, so now we already have these two expressions, so we can solve these expressions. And then if you solve these two expressions, what you are going to get is something like this. So your sigma x can be written as now E divided by, this will be 1 plus mu, okay, this will be 1 minus 2 times mu. Okay, so you just have to solve this. Okay, then and then only you will be able to get this. And this will be epsilon x, okay, plus mu times you will be getting epsilon y. This is one expression you will be getting. And sigma y can be obtained something like 1 plus mu, this will be 1 minus 2 times mu into, this will be mu into epsilon x plus this will be 1 minus mu into epsilon y. Okay, so this is expression A and this is expression B. Okay, we also know that the gamma uh, xy can be written as tau xy divided by g, because the other shear term, that is the gamma xz and gamma yz, it is 0. Okay, so what we can do is you can rewrite the same expression like what is tau xy. So tau xy is nothing but g into gamma xy, and we also know the value of g is something like E divided by 2 into 1 plus mu into gamma xy. Okay, so what we can do is we can multiply and divide the same term like this, that is I am writing down something like 1 minus 2 mu. Okay, and here also I am writing 1 minus 2 times mu, and same thing I am writing, that is E, this is 2 into 1 plus mu into gamma xy. Okay, so if you rewrite this particular term, so what you are going to get is E divided by 1 plus mu 1 minus 2 mu, okay, into, you have 1 minus 2 mu divided by 2, okay, into, you have gamma xy. Okay, so now basically what you will find in this three expression, so this is a constant. Okay, so this I am just taking down all these values as a constant so that I can write it in form of a simple matrix the way I have written earlier. Okay, so this is nothing but your constant. So let me write down the expression now for the matrix. Okay, so now you have sigma term. So sigma will be having now three components. One is sigma x, one is sigma y, and one is the tau xy. Okay, so this can be written in a simple form, that is E. Okay, so this is a constant, so this is 1 plus mu and this will be 1 minus 2 times mu. Okay, so same thing can be written over here as 1 minus mu, this will be mu, this will be 0, this will be mu, this will be 0, this will be 1 minus mu, this will be 0, this will be 0, and this is nothing but 1 minus 2 times mu divided by 2 multiplied by, now you will have epsilon x, epsilon y, and gamma xy. Okay, so if you go for the multiplications over here, so if you see the expression A, so expression A is sigma x. Okay, so you can see sigma x is the product of 1 minus mu into epsilon x. So here you can see this is 1 minus mu into epsilon x plus mu into epsilon y. So you can see mu into epsilon y, and there is a 0 term. So 0 into shear term, shear xy. So it will be 0. Similarly, if you see the expression B, so it is nothing but mu into epsilon x. So here you can see mu into epsilon x. Here 1 minus mu into epsilon y, and shear term is 0. And as far as the other part is concerned, that is shear part is concerned, so you have no contribution of epsilon x, epsilon y, and you have only 1 minus 2 mu divided by 2 into gamma xy. Okay, so this can be written in a simple form as a D matrix. Okay, so this is nothing but your D matrix. Okay, so in short, what you can have, this is sigma equals to your D matrix multiplied by you have a strain matrix. Okay, so this D matrix is nothing but your stress strain matrix, which is relating the stress and strain for a plane strain condition. Okay, so this is a different matrix than the matrix which we have seen earlier for the plane stress condition. So if you see the plane stress condition, you have a constant of E divided by 1 minus mu square outside, whereas over here this is E divided by 1 minus mu, sorry, 1 plus mu and 1 minus 2 mu. And as far as this matrix is concerned, the coefficients are also different. Okay, so depending on the type of the problem, whether it is plane stress problem or plane strain problem, the value of D matrix is going to change. Okay, so sometimes in the examination this derivation is asked, that is you have to derive the stress strain relationship for plane stress condition or maybe plane strain condition. In that particular case, you have to just start from the basic and you have to get the derivation done. Okay, lastly there is one more term, that is axisymmetric case. Okay, so derivation part and the justification part we will be covering when we will start the axisymmetric problem. Okay, so I am stopping here today, and we will be continuing tomorrow with the derivation of the CST element, which is used for the analysis of 2D problems. Okay, are there any questions as far as this part is concerned? It was just a derivation part. Yes, students, are there any questions, please?
No, sir.
No, sir.
Okay, then. So I